I will continue with the lectures of Professor Kolountzakis on orthogonal Fourier analysis of domains and tiling problems.
Thank you for being here still. So let me very quickly run over the slides of the previous two lectures so that I remind some things, and to those of you who are not there, it will not be completely boring. So last time I went through the basics of Fourier analysis on an interval or on a cube where we have frequencies, like for instance when you do Fourier analysis of the unit square, you have the integer frequencies which are enough to do your Fourier analysis in what sense? That the corresponding exponentials with those frequencies form an orthonormal basis. They are orthogonal and complete in L2 your shape. And the general question is, on which kind of domains can one do this? Can one find an orthogonal set of frequencies which is complete, an orthogonal basis? And some of the examples that we started with last time are these. So on the first row you can actually do it. On the second row you cannot. We proved some of those. And here is an example that I showed you with a domain which has an unusual set of orthogonal frequencies. And then we stated the Lattice conjecture. The Lattice conjecture says that you can do this in a domain, you can find an orthonormal basis if and only if this domain can tile space by translations, meaning you can take your domain, translate it to some locations, not rotates, but just translates, and fill up space exactly once everywhere. And starting from this, okay, this was the motivation of Fourier. We started asking ourselves, what does it mean to tile, and especially what does it mean to tile when you look at it from the Fourier side. And from the Fourier side, when you have to tile with a function f, so you have a function f, you're moving it around at the locations t, and you get a level L, constant everywhere. What it means, if you look on the Fourier side, it means, okay, this is Fourier's conjecture in geometry 9. On the Fourier side, tiling means exactly this. So f is your tile, what you move around. And you look at this Fourier transform, you look at its zeros, and delta t is a point mass on each one of the locations. You can view this as an infinite measure, which is a tempered distribution. Therefore, its Fourier transform is well defined. And what you want is that the support of this tempered distribution lives on the zero set. So if these lines, these curves are the zero set, your tempered distribution lives on those curves or in higher dimensional surfaces and so on. So this is what it means to look at tiling on the Fourier side, and then go back and see what the Fourier conjecture can be, how the Fourier conjecture can be restated in completely geometric language. So we saw that Fourier's conjecture is equivalent to this statement in blue. So what does Fourier conjecture say? That a domain omega tiles at level 1, so this is the ordinary kind of tiling, it tiles at level 1, if and only if its Fourier transform squared, which we usually call the power spectrum of the domain, its Fourier transform squared tiles with some other, not the same translations, but can tile at this level. This is completely equivalent, and we saw why. So in this language, Fourier conjecture makes more sense because both sides refer to it tiling by translation by different objects. So omega tiles if and only if its power spectrum tiles. This is the Fourier conjecture. We saw why this is true. Therefore, we started looking at this Fourier conjecture through the prism of this tiling in Fourier space. And then I started giving you some examples. The first example I gave you was a problem from the so-called Scottish book, which was the following. Steinhaus had asked if one can find a positive, strictly positive everywhere analytic function which tiles the real line when translated at the integers. This is the question of Steinhaus. And the interesting thing for us that the proposed solution, or the proposed candidate for solution, e to the minus x squared, had no hope in the world to ever do this, because the Fourier transform of f, of this f, maybe I'll do this again. the Fourier transform of this f has absolutely no zeros because its Fourier transform is itself. So no zeros. If you don't have any zeros in your Fourier transform, you have no hope of tiling by translation. Because tiling by translation means that on your Fourier zeros, something lives. Tempered distribution lives. If you have no Fourier zeros, no tiling. So that was the first problem we looked at. And we also actually saw what the solution would be. The solution would be to define f on the Fourier side by adding two triangles with incommensurate bases and narrow enough to be inside -1, 1. That was the solution. And then I made the remark that everything that I had said so far, if you restrict it to tiling by z, it's just the so-called periodization of a function in another language. The periodization, most of you, I'm sure, you're already familiar with. And we just did this again in this old language instead of the new language. And then we talked about tiling by a lattice. So when you're tiling by a lattice, you have a lattice and it's dual lattice. So when this gets spread out, this one moves in and becomes denser. They're connected by this linear relation. And we stated the Poisson summation formula in distribution language, which means what? That if I put a point mass on each one of those points, and I Fourier transform this, I will get a point mass, same point mass, on each one of those points. That's the Poisson summation formula in this fancy language. And we use this to prove Fuglede's conjecture in the lattice case. What is Fuglede's conjecture in the lattice case? It's the following, if and only if. Omega tiles by lattice translation, if and only if its power spectrum tiles by lattice translation. In fact, it's even more specific. When omega tiles with lattice T, then omega has spectrum T star. Okay, and we prove this without any doubt and in every detail. It's these few lines. Okay, so we have lattice Fuglede. What do we do then? Another example from how looking on the Fourier side at the problem of tiling can help you prove stuff. And this example was how to fill a box with two types of bricks. So you have a large box, Q1, Q2, Q3 are its dimensions, and you have two big piles of two types of bricks. The red bricks and the blue bricks. The A are the red bricks and the B are the blue. And you want to fill the big box. By fill, I mean no gaps and of course no overlaps. The bricks come into each other. And the theorem here, which was first proved in combinatorial ways, was that the only way you can hope to do this is if you can actually cut the box in one of its dimensions, cut it, and fill one half or one part with the blue brick and the other part with the red brick. There's no other clever ways to use two bricks to tile a box that you cannot do by just splitting the box in half and using one brick here, the other brick there. And we proved this. So this is an example here. This is one filling of the big box with these two bricks, and this is what it implies, that you can actually cut one dimension and fill one box with one part with a blue brick and the other with just red. And this is general. You can always do this. If you can fill it in any way, then you can fill it in such a way. And we proved it by looking at the Fourier zeros of both the bricks and the box, which are very explicit. You can compute the Fourier transform. This is in two dimensions. You can compute the Fourier transform precisely. You can find the roots of the Fourier transform exactly. And then we did some tricks, some calculations, and we finally proved that you can do this. I'm not going to repeat it. And we saw that the same theorem is not true with three bricks. There are boxes, big boxes, that you can fill with three bricks. But you cannot cut this box and fill with fewer bricks one part and fewer bricks the other. Okay, and then we proved the following result, back to Fuglede projection now, but just as the case was with translational tiling, if you look at the symmetric in the convex domain, and you ask yourself, is it spectral? Can I find an orthonormal basis of exponential in the convex domain? Let's say this K. A convex domain cannot tile by translations unless it's symmetric with respect to some point. So a triangle, no matter how hard you try, a triangle will never tile by translations. It can tile if you allow me to flip it. But if you don't allow me to flip it, it cannot tile. And this is general. So, and this was the theorem of Minkowski, which we proved. So the theorem of Minkowski is this one, that the convex translation tiles must be symmetric. We proved this using the Brun-Minkowski inequality, which I described in the previous slide. And then we proceeded again using the Brun-Minkowski inequality to prove that any convex spectral set is also symmetric. So a triangle is not spectral. You cannot find an orthonormal basis of exponentials for a triangle. Okay, this was our proof, more or less. And then we moved on to the disk. And I gave you a proof in 2 dimensions that the disk cannot be spectral. So the Fourier zeros of the disk, since the disk is rotationally symmetric, the Fourier transform is also rotationally symmetric. So its zeros will be circles around the origin. So it will be some circles. And what we really care about is the first root, R0, which is very well known because these are the zeros of the first Bessel function. And it turns out that this is the first zero, 1.08 and so on. And we notice that if you place, since the basic fact which I really want to repeat now is that if you have 2 orthogonal exponentials, lambda 1 and lambda 2, so these are the frequencies of the exponentials which are orthogonal with respect on this domain. So what must be true, and this is usually the first line of attack on these problems, is that their difference must belong to the zero set of the Fourier transform of your domain. So in our cases, the zero set are those circles. So what this means in the case of the circle is that the Euclidean distance between any 2 points of the spectrum must belong to this set. R0, which is 1.08, and so on, R1, which is the next guy, and vice versa. So this is a necessary condition for the spectrum. Any 2 points must have distance at least 1.08, at least R0. So if I place a disk at half this quantity as the radius, all these disks are non-overlapping. So this is what we call a disk packing. Packing means you have the objects and they don't touch each other. But disk packings are well known since 100 years ago to have a maximum density. Density is, look at a big area, how much area you have managed to cover divided by the total area. They have a maximum density of 0.906. And then we observe that if lambda is a spectrum of the disk of, say, radius of area 1, it's always the case that if you have a spectrum, the density is the area or the volume of the domain. So if we took our, as we did, if we took our disk to have area 1, the density of lambda is also 1, which tells us that the density of this tiling, by calculating the numbers, is actually not 0.090, but 0.91, which is higher than this, and that's a contradiction. You cannot have this dense packing. So this proves that the disk in 2 dimensions is not spectral. You cannot find a spectrum, because if you could find a spectrum, you would have a very dense packing of disks. This proof does not work in higher dimension, but I gave you a proof about why a smooth convex body in any dimension cannot be spectral. And of course, it definitely cannot tile, because if you have a smooth body, it's impossible to fill the gaps, right? They never touch well enough to close all the holes. So we proved this using a result of geometric Ramsey theory. It's a very well-known result that in its simplest form says that if you have a dense enough set in Euclidean space, then beyond the point, all Euclidean distances will be implemented by your set. So there's a number, say L0, such that for every L larger than L0, you can find 2 points of your set with precisely that distance. So we use that result, not for the Euclidean distance, but for the distance that arises from the polar body. and we arrived at a contradiction. And from that point on, I started mentioning several existing results in the conjecture. One of them was that almost from the beginning, we knew that if you have a convex set which tiles, then it must be a polytope, and it also tiles by a lattice, and therefore by lattice Fugletti, they are spectral. So for the case of convex bodies, we knew from the very beginning the direction tiling implies spectral because of the work of these people. And then this is a result of mine which I already proved. I mean, I went through today that every convex spectral body must be symmetric. This is the next result I talked about, that smooth bodies cannot be spectral. And then there's a result by Mihalis, Katz, and Tau that for convex bodies, the conjecture is true in dimension 2, meaning the only spectral convex bodies are the only convex bodies which can tile, which are parallelograms and symmetric hexagons, nothing else. And then this is another result. Okay, I'm not going to go spend too much time on this. Here is a result. Let me say here directly that if your domain is in one dimension and consists of two intervals, like this, then the conjecture is true. This is a result of lambda. So this set can tile the line if and only if it is spectral. And the annoying thing here is that if you allow yourself three intervals, it's almost known, but not precisely. So one direction is known, a spectral tiling. So if this is a spectral set in one dimension, then it must tile by transformations. But in the other direction, we do not know it completely. We know it under some assumptions. And I think this is one of the open problems that I will mention, which is very ripe for a solution. But it's not trivial. If you don't do it, if you don't get a clever idea for this, it very quickly becomes a wildly branching tree of cases regarding the lengths and the locations of the intervals, and it's unmanageable. And this is how Terry Tau proved in 2003 that the Fugletti conjecture is actually not true in high enough dimension. What is high enough dimension here? He proved it for dimension at least 5, but then other people, including myself, have lowered this dimension to 3. And also myself and, okay, we did this for 3 and 4. And also in the other direction, about a year later than this, myself and Mathematology proved that the other direction is also not true. And again, the dimension goes down to 3. And the end result, until now, is that the conjecture is open in dimensions 1 and 2, and in both directions. No other, I mean, the general conjecture is known in all other cases. But in these low dimensions, it's not known in either direction, to be either false or true. And if you ask my opinion, the hardest case is d equals 1. Because almost every result that you look at d equals 1, and very quickly leads you to number theoretic questions. And they can be quite hard, especially for analysts. So, new stuff. So what am I going to talk about today? So last time I explained to you in at least 2 ways why the disk is not spectral. But more is true. Okay, the first, it was proved by Mihalis, Katz, and Peterson that the disk is not spectral. Fugletti himself and Mihalis and Rudnev proved that not only that it's not spectral, but the disk, if you find any orthogonal set for the disk, it's going to be finite. You cannot find an infinite orthogonal set of exponentials for the disk. This is says a lot more than it's not spectral. If it were spectral, not only you would have an infinite set, but you would have a set of positive density equal to the volume of the disk, to the area of the disk. But that's not possible. They must always be finite. But we still don't know. If there is a uniform upper bound for the size of those finite sets. I mean, by these two results, it's conceivable that you could have arbitrarily large but finite sets. They would not one contain the other, but for any number you told me, I could find you n orthogonal exponentials. But any fixed collection of orthogonal exponentials would have to be finite. We strongly suspect that not only there's a uniform bound, but the bound is 3. Many people believe that you cannot have more than 3 orthogonal exponentials for the unit disk. Why can we have 3? Because look at the, okay, this is the spectrum of the zeros of the disk. Look at R0, which is the first one, or any other one you want. And just take 3 points, take an equilateral triangle of distance R0. Okay, then pairwise, these 3 points have a distance which is R0, therefore they satisfy this, therefore they are orthogonal, and here's your 3 points. And almost everybody believes you cannot add a 4th point here. Okay, but no one knows how to do it. So what am I going to talk about now? Since people did not know of a uniform bound, they tried to get some quantitative information. I mean, saying that something is finite is a nice piece of information, but it's not quantitative. What can we say more? And what the first result about this was by Mihalis and Kolountzakis, who proved that if you have any orthogonal set for the disk, and you look at how many points it has at distance r from the origin, say in a square minus r to r, then it has linearly many in R. This confuses sometimes people because we know it's finite. But still, this means that take any lambda you want and look at this quantity. There is a fixed constant such as this is less than c times r. This is not contradicted in the fact that it's finite. Okay. And again, let me say that if this were actually a spectrum, this quantity would be of the order of r squared. It would have density. Okay, but it's much less. It's of the order of r. What I'm going to say now, and I will describe this to some detail, is an improvement of this result by Mihalis and myself, that the bound, which is order of r here, can be reduced to 2/3. And we don't know if that's optimal. We believe it's not, but we don't know how to do it. And this bound arises in the following way. We take any spectrum lambda, any orthogonal set lambda, and when we look at delta, capital delta is the smallest distance between, I mean, it always exists, it's a finite set, the smallest distance between 2 points. And then we prove that the number of points is of the order of delta. So if you want to have too many points, you better spread them far apart. Okay? If delta is small for 2 points, then the total number is going to be small. And from this, it's easy to see, or we can get this, we'll see this. So now I will start describing to you how to get this inequality. Okay. So the Fourier transform, and we know that 2 exponentials are orthogonal if and only if the difference of the frequencies is in the 0 set of the Fourier transform squared. So if you have an orthogonal set, the differences must live in the circles, which are the zeros of 1d hat. These are the zeros of 1d hat, and they come at increasing distances, and we know a lot about these numbers. This is what we know. We have asymptotic estimates, very good asymptotic estimates for the roots of the Bessel functions. These are very classical estimates in analysis. They are typically done in any course in the Fourier transform where you learn the method of stationary phase and how to estimate integrals. They have been used many, many times by people who are studying problems of how many lattice points do you have in dilates of a disk or something else. And here they are. So the nth root is at about 1/2 n plus 1/8. This is crucial, actually. This offset of 1/8 is very crucial. Plus an error which is estimated by 1/n. And not only we know where the zeros are, we also know about their differences. You might think that, okay, if I subtract Rm minus Rn by this, I will get an estimate. But you can actually, you know a better estimate. If you subtract 2 terms which you know only this about, you'll end up with 1/n. as their sum or difference. But you actually have 1 over n squared. The estimate is much better than what you would get from this. So if you subtract Rm minus Rn, you get the difference of the main terms. So you subtract these and you get 1/2 m minus n. But the error term here improves, which is kind of seems strange. But you don't get this error term by subtracting these two. You get it anew with the method that was used to estimate this. Where notice that n is the smallest of the two. So you cannot just hold n fixed and let the other guy go to infinity and expect to get something here. They both must go on. Anyway, by using, let me make the following observation. By just looking at the first one, if we just look at the first one, then and you assume you have 3 points on the spectrum, you immediately see that you cannot have 3 points of the spectrum on a line. Why? Because this distance would be a half integer plus an eighth, this distance would be a half integer plus an eighth, and so should this be. But it's not. If these are half integer plus an eighth and half integer plus an eighth, then this is half integer plus a quarter, which is not of the form half integer plus an eighth. So you cannot have them on a line. And we actually make this a little more quantitative, and we look at how close they can be on a line. What do I mean? If you look at A, B, C, the 3 points of the spectrum, how small can this angle be? Okay? And it has a definite lower bound. The lower bound that we can prove is that if you assume that all the distances here, from A to B to C, are at least R, so R is the smallest side of the triangle, then the angle here is at least 1 over root R. Because if you try to bring this point too much down here, it begins resembling this case. At some point you're going to do it. And the right point is 1 over root R. So if you have any triangle formed by 3 points of the spectrum, all the angles except for the smallest one, so the 2 biggest angles of the triangle must be at least this, or all the external angles are at least 1 over root R. And what does this give? Okay, now let's do it, see what this implies about how many points they can have in a strip. So suppose you have a strip of width, let's say root L. And then you have 3 points in the strip of distance at least L in pair. So you have 3 points in a strip whose distance is at least L, and the width of the strip is root L. This cannot happen because this contradicts, this forces the angle theta to be less than 1 over root L. So if you choose the right constant, then you get that any strip of this width, no, remember, delta is the minimum distance of any 2 points. So any 2 points are at least delta apart. So any strip of this width, you can only have 2 points in it. Because if you had a third point, it would contradict this. So any strip of root delta width will have 2 points. And then it's easy to get the first result by Mihalis Kolountzakis. Here's your square, r by r squared. You split it into disjoint strips of height root delta. How many do you need? R over root delta. Each of them has 2 points. Therefore, the total number of points will be the number of strips. This one. Okay? So each of them has 2 points. So that's how much you have. Now, delta is at least 1. That's very easy to see. It's a constant. So this is of the order of r. So delta is at least 1. So this is of the order of r. This is the US of a trillion. Delta cannot become too small because delta is bounded below by this R0, the smallest zero of the Fourier transform of the disk. So we recovered the result by US of a trillion, and by being a lot more careful, we will get the next result. So here is what we do now. So we fix 2 points, minus v and v, and we assume these are 2 points on the spectrum. This is very easy to do. Just pick any 2 points, almost at this smallest distance, and you put your axis there. Okay, so I can assume that, okay, delta is my smallest distance. I can certainly find 2 points which are at most 2 delta apart. And so let's see, these are the 2 points. Now look at another point. So minus v, v, and lambda are 3 points on the spectrum. Now, if I look at the hyperbolas defined with this and this focus, minus v and v, every other point in the plane will belong to one such hyperbola. So let me draw this hyperbola going through the point lambda. It's going to hit the axis at a lambda. We'll just call it a lambda. And what turns out to be the case is that by looking at the definition of the hyperbola, which says that the hyperbola is the locus of the points whose difference of distances from the foci is constant, it turns out that the difference of distances from lambda to the 2 points is the same as this difference, this minus that, okay, which is twice a lambda. And since we know that the difference of distances, this is the Rm minus Rn, asymptotics that I talked about, since we know this estimate, we end up with this number twice a lambda being k over 2 plus an error. K over 2 is half an integer. How many half integers are from here to there? About 2v, or 4v. Okay? And all the a lambdas are not exactly on those half integers, but they're very close to those half integers. And the farther out you go, the closer you are. Okay? So here we are. The only hyperbolas that matter in this business are those who go through exactly, who pass through a half integer point here. The hyperbolas that go through the points of the spectrum, the black line, will fall very close to that. They're not on that necessarily because of this error term, but they fall very close to that. So we have about 4 delta such hyperbolas. And every lambda is near one of those. What do I mean by near one of those? If you look, so suppose that this is one of the exactly half integer hyperbolas. So this is some k over 2. Where is my lambda going to be? It's lambda going to be maybe here. What we prove is that if you go beyond this distance from the origin, delta to the 3/2, that's what we must do. So if you ignore a disk here of radius delta over 3/2, if you take all the lambda which are farther away than this, then if you take the asymptote of this hyperbola, we know hyperbolas have asymptotes, right? You take the asymptote of this hyperbola and you increase, you take a strip around that asymptote by delta, this order of root delta. So everything is going to be outside this disk. All of the spectral points are going to be in these strips. So for each one of the 4 delta hyperbolas, you have the delta to the 1/2 strip. Everything's going to be in there. But every strip of this width has 2 points in it. Every strip of this width has 2 points. So all the points of the spectrum which are outside this disk, how many do I have? You're going to have as many hyperbolas, 2 for each one of them. That's order of delta. But then I still have to count those guys, which are inside, for which I cannot use this. Well, for these guys, I will use the Iosovich-Spermine bound. So in the disk of radius delta to the 3/2, I have this bound by the Iosovich-Spermine method that we proved before. And Right. So if you take R to be delta to the 3/2 and you plug it in there, you get again order of delta. So this splitting point is what gives you order of delta outside and order of delta inside. Total order of delta. So that gives us the result, order of delta. The number of points is order of delta. So from the strip covering, this is the Joseph-Germain bound that we got. You have this. From the new bound, we have that one. When delta increases, this one increases, that one decreases. The best bound is the minimum of the two, and you find it where they coincide. Where they coincide is for delta equal to delta to the 3/2 is equal to R, which means that delta, and therefore also this, is going to be R to 2/3. Now this is the best we know so far. I strongly believe this result can be improved. I have tried sometimes, but I failed. But this, I think, is also one of the problems that I consider as ripe for improvement. The methods are very elementary, but sometimes you have to be careful with the asymptotics to get out the right numbers. Now, let's change our setting completely. If you remember, I told you that tau disproved the Fourier conjecture not by working directly in Euclidean space, but by first working on a group. In particular, he worked on this group. And I said that the Fourier conjecture, the notion of a spectrum and orthogonality, all these make perfect sense in locally compact abelian groups. And the easiest case to work in are the finite abelian groups, which have a very definite structure, we know how they look like, and all the real problems already appear here. So, one direction that research has taken recently is not to work on the Fourier conjecture in the Euclidean case and try to get better and better results, but to alter the group. Say, okay, I cannot prove or disprove the Fourier conjecture in Rn, but maybe I can prove it in some class of abelian groups. Certainly the simplest class is the cyclic, finite cyclic groups. Okay, and what is the simplest cyclic group? The ZP, or P is a pi. Okay, so what does the Fourier conjecture say in the case of ZP? ZP is a cyclic group of P elements. It's obvious that the only object that can tile ZP is either a single point or the whole group. Because if you take any subset of ZP, if it could tile ZP, then P would be divisible by the size of the set. And only one and P can do this. So, we only have trivial tiles in ZP. For the Fourier conjecture to hold, this would also mean that we only have trivial spectral sets. Only the point, single point, and the whole group are spectral sets. And indeed, let's see why this is true. So suppose we have a spectral set E, it's a subset of ZP, which has two or more points. What is the Fourier transform of 1E hat? Well, to complete the Fourier transform, you just add the corresponding character corresponding to nu. The character here will be this function, E, to the 2 pi nu, so the function was gamma of x, nu x over p. Okay, which you can view if you take this and call it nu. You can view as a power, just a power of this number. These are roots of unity. Okay? So, let's look at this quantity here. We have a number zeta nu, and this is a polynomial in zeta nu. Agree? It's just powers of zeta nu. It's a very simple polynomial. Some powers of zeta nu. Therefore, zeta nu is the root of that polynomial. But zeta nu is the pth root of unity. When you have a complex number which is not a rational number, or even for rational numbers, you have its so-called minimal polynomial. It's the integer coefficient polynomial of smallest degree of whose root it can be. So for instance, the minimal polynomial of square root of 2 is x squared minus 2. Okay. The minimal polynomial of the pth root of unity is very well known to be the p cyclotomic polynomial, as we call them. And it's just this. If you plug in place of x any one of the pth roots of unity except for one itself, it will vanish. So these will be all systems of a degree p minus 1. The pth roots of unity will be exactly the roots of this polynomial. And what do we know about the minimal polynomial? That if you have any other integer polynomial which has that root of unity, it will be divisible by phi p. So put any polynomial you want here which is 0 at zeta nu, it will be divisible by phi p of x. But look at phi p of x. It has 1 on every place up to p minus 1. What does it mean to divide? It means that if you look at it, if this is the base polynomial, you can make it up by adding essentially copies of that with coefficients around. This is what it means to multiply polynomial. But since the coefficients are already 1 and you need to leave, and this is your polynomial which already has coefficients, it must be filled by this one. There's only one thing you can do. You can take this polynomial itself. There's nothing else divisible by this of degree p minus 1 or less. So this proves that the only spectral subset of ZP is a single point and the whole group, exactly as it is with a tile. So we can restate it as follows. The Fourier conjecture is true for the group ZP. There's no big deal, but at least we know that there are groups for which it's true. And we'll see there are others. But I would like to repeat a little bit what I said about the algebraic part of the proof. So let's look at, say, the 12th roots of unity. The 12th roots of unity, if you look at them at the unit circle, you can order them like this. They split, because 12 is not a prime, they split into so-called cyclotomic classes. What does it mean? That for instance, let's take this one, 1, 5, 7, 11. So this point, this, and that, which happen to be the vertices of a rectangle, they are algebraic conjugates. What do algebraic conjugates do? They behave like 1 as far as integer polynomials are concerned. If an integer polynomial vanishes on one of them, it vanishes on all of them. They move as a block. So when you're asking questions about the roots of your Fourier transform of a set, which is a polynomial, you are either going to include this guy entirely, or you're not going to touch it at all. So all our zero sets will be unions of cyclotomic classes, which restricts the form of the zero set a lot. And this is what, basically, it's this property and several more high-tech variations of this that are exploited by all these results, which I don't want to go through individually. All these results in the recent years, where people prove that the conjecture is true, sometimes it's false in a certain class of groups. So the first one is ZP to the m. So if you take any cyclic group whose order is the power of a prime, then the conjecture is true there. It's not trivial. It's not like ZP. I mean, because you have more cyclotomic classes. And then Laba herself, perhaps in the same paper, she proved one direction of the conjecture, the tile spectral, in the case where you have a cyclic group with 2 different primes only. This is a nice result. It's not very hard to. You go from ZP cross ZP. You not find an abelian group, and the Fourier conjecture is true there. I guess this must be one of the first results where people really started varying the group. And there's a whole bunch of results, like true in ZP cross ZP square. You can do all sorts of things and variations there. You can write papers to no end. I've written some of them. Here's a case where it's false. So ZP to the fourth, the conjecture fails, which is not unexpected. It also fails in part to the fourth. And then people have been trying to put more and more primes into higher and higher power. I don't think I'm going to make any more, give any more detail about this. Okay, this we already talked about. That if a convex polygon tile space, then it must be symmetric. But I also told you last time, not today, that Minkowski didn't just prove that the body is symmetric, but also its faces, for dimension 1 faces are symmetric. So you cannot ever have a tile that looks like this, because the face cannot be a triangle. Now, as far as spectral bodies are, this was proved by Greenfeld and Lev in 2016. So if you have a spectral convex polytope, not only it's symmetric, we already know that, but it must also have symmetric facets, or symmetric codimension 1 faces, exactly as is the case here. Okay? And Greenfeld and Lev also proved the spectral implies tiling conjecture, which was the one that's missing in dimension 3 for polytopes. So with this result, the Fourier conjecture was known to be true for convex polytopes up to dimension 3. And this is a related result, not exactly tiling, but so I'm not going to insist too much on this. It's about equidecomposability of a body. So there are some bodies that you can cut up and find them into pieces, move around, and make something else. That's equidecomposition. And this is the major result of the last, I would say, 10 years, maybe even more. Major result is a result by Lev and Matolchi in 2019. This was published in Acta Mathematica. But the conjecture is true for all convex bodies, actually not just polytopes, all convex bodies in all dimensions. Which was, people were doing, even Lev himself, were doing incremental things, raising the dimension, but at some point they hit on the right idea and they proved the whole thing. And I will say a few things about that. Now, here's a related question. If you take a product set, so in Rm cross Rn, you can take a set A here and a set B here and cross them. You have a product set, A cross B. It's very easy to see that the product set tiles if and only if the components tile their corresponding space. That's very easy to see. Does the same result hold for spectral? So it's easy to see that if A is spectral and B is spectral, lambda 1 and lambda 2, you can cross the spectra and you get a spectrum of A cross B. So one direction is true. So if A and B are spectral, A cross B is also spectral. But what about the other direction? This is still unknown. If A cross B is spectral, do we know that A and B are spectral? If you get a disproof of this one, then you immediately have another disproof of the Fourier conjecture, because this is a property that tiles have. If you prove that spectral sets don't have it, you have to disprove the conjecture, right? With a new proof. But there are some affirmative results here in several cases. In fact, I have not updated this because of even more results. Greenfeld and Lev proved that this is indeed true if one of the components is an interval, and then shortly after that, I proved that you can take A to be a union of any two intervals. And then Greenfeld and Lev did something very good here, that they could prove that if this space is R2 and A is a convex polygon, then yes, it's true that A is spectral and B is spectral. And lately we have a paper with Lev and Matolchi that we raise this exponent to any n. Here's another property of the spectrum, but I really don't think I have that. Oh, okay, there's a nice story here. Maybe I will say the story. So, if you have in dimension 1, you look at all the tilings by a function, f plus t. It turns out that all these tilings, if f is of compact support, like the indicator function of a bounded set, all these tilings must be periodic. This is somewhat easy to see when you're looking at tilings of the integer by a finite subset of the integer. This was an old result by Don Newman, who proves that if you have a finite subset of the integers, and this finite subset can tile the integers, let me denote it like this, the set of translates T, then this set of translates is periodic. This is a result of, it's easy actually to prove using combinatorics. But when you try to do it for a function in the continuous setting, it's not easy at all. And the first result that was proved in this, which I have not listed, I should have, was by Lagarius and Wang, and they had sort of mimicked this proof in the measurable setting. But then myself and Lagarius discovered a method for harmonic analysis using the so-called idempotent theorem of Paul Coyne, who happened to be my advisor, where we proved that this this is periodic in a much greater generality. So this was actually the paper that got me started on this business. I did when I was a couple of years after my PhD, and I started proving stuff, and I got, well, basically a big fraction of my career has to do with tilings. And I want to mention the fact that maybe 10 years after I wrote this paper, I somehow learned, somebody told me, that they had actually done it before us. So Leptin and Detlef Müller had actually proved the exact same statement with the exact same proof as we had. I didn't know, because if you look at just the title, but even the front page of the paper, it's very hard to see that it has anything to do with tiling. But it is. So if you read it carefully, you see it's exactly the same proof. And what I often say is that it's sometimes good in mathematics not to know. Because if I knew at the time that this result already existed, maybe I would not have gone into this field and I would not have proved all this stuff. It's good not to know. Of course, once you know, you must always clarify that you were not the first to do it. And I always do so. But sometimes not knowing is better in mathematics. Okay. And so is this true for spectra? Because a spectrum is also a kind of tiling. So for omega to be spectral, it also means that this tiles. So does this theorem apply? No. Because this guy here is never of compact support. When omega is an indication, this is never of compact support. Because if it were of compact support, omega would have to be, the indicator function would be continuous, which is not. Yet, it took a while to find counterexamples. Myself and Lev found a counterexample of tiling of the line without any periodicity. Of course, the function f would have to be unbounded support. And myself and Josevich, this is, I think, one of our best results. We proved that in the line, for any bounded set, every spectrum is periodic. It had been done for unions of intervals by Bose and Madan and myself before that, but we found the right approach in 2011. We proved that all the spectra are periodic in the line. Of course, it's not true in higher dimension. Neither is this. Okay, this is what led Lev and Matolci to prove the conjecture for complex polytops. They made the following, I wouldn't call it observation, it's really a theorem, but if you look at it in the case of finite groups, it's an almost obvious theorem. But in the case of Euclidean spaces, you need to do some work. But it says what? That if you have a spectral set, omega, then it has the following property. It can tile its complement if you allow weights. So I can find a non-negative measure mu, these are the weights, such that if I convolve omega with mu, which what does convolution do? Mu has some points with weights. So take omega, put it there with this weight. Take omega, put it there with that weight, add them up, and you get the complement, the indicator function of the complement. So for instance, a square can certainly tile its complement. You can put a square here, a square there, and so on. Can a disk tile its complement? No way. You cannot. So this is what they used to prove that if you have a spectral complex set, then since it must tile its complement, first conclusion is it must be a polytope, otherwise, if you have any curved part here, the only thing you can place near it will be curved like that and they will never match. So first prove it's a polytope, and then after that, it was not too hard to prove that it tiles. So that this kind of weak tiling, as we call it, is actually a real tile. But I want to show you how this approach immediately gives, for instance, that this set is not spectral, which before this theorem we could not do. Okay, if you have such a domain, you can never tile its complement, which includes this hole, by placing copies of this. Because if you try to place anything in here, it's going to overlap this guy, which is not allowed to do. Because you must tile the complement, and only the complement. And another approach of this would be, for instance, the two interval case in the line. If you have two intervals which are like that, so if this hole here is less than this, you can never weak tile its complement. So that immediately is not spectral. And one of the big hopes here, which again has proved to be hoping more than we could do, is to use this approach for three intervals. So use this weak tiling approach to prove that anytime you have a three interval set in the line, which is spectral, that it actually tiles. So if you have this in its spectral, you know from that theorem that its complement must be tileable by this set, which is a very strong property. But we have not been able to do it properly and conclude that it's tiling. But I believe it can be done. I mean, even others believe so, not just me. So if you want to try your teeth on something, try this. Assume you have three intervals which can tile their complement in this sense with weights. Prove that they actually tile properly. We can tile the entire real line with whole copies of these three. Now, there is more here. This is about justifying weak tiling in the finite group case. Why does it? But I think it's a little too much for an hour. This has to do with respaces, which I certainly don't have any time to go into. So I think I will stop here.
Thank you. Any questions or comments?
So the problem is here because you have tilings, so you know already you have tiling with weights.
Yeah, so assume that I can fill up the complement of this set by translating this set at some locations with weights, positive weights always. Prove that I can actually fill it with whole copies. Looks like child's play, but it's too much bookkeeping to do if you don't have the right idea of how to do things.
But with the weights, they can overlap them.
They can overlap with each other, but not with this guy. So you can tile its complement. You're not allowed to touch this. You have one copy of the set, which you're not allowed to overlap, and then you take several weighted copies and fill up the rest.
But if they overlap with each other in the complement,
that's fine, as long as the sum is 1. The sum of the weights at each point. So each point will be hit by several copies. If you add the weights at each point, it must be 1.
But this you have from the weak tiling.
This is the weak. Okay, so suppose call the set omega. Then if you assume it is spectral, then it follows from the Lev-Markovitch machinery that omega can weak tile its complement. And I want to prove from this, not really looking at this at all, I want to prove from this that omega can tile the real line. By copies, whole copies, not weak tile, ordinary tile. This is what seems to be within reach, but it's not.
And why 3 intervals? So if you have 4 intervals or 5, this is.
What can we do with 4? But
this is considered
3 is the first case when it's not known.
Maybe 4 you can reduce to 2. No?
Again, that would be very nice bit.
Other questions?
Sorry, I have a question. Of course, the topic is very, very interesting, and I have many questions. But I saw one theorem that you present that was that took my attention was that you have one subset of RD, which is convex, then the reverse measure of K minus K, yes, has this lower bound, yes.
Yeah, that's the Bruni-Kosky inequality.
Yes, that one. Is this related with these properties of the Hardy-Limit maximal function that you want to take the centered maximal function with both, associated with both?
Yeah.
Then one has very good, let's say, mapping properties of the Hardy-Limit maximal function. But if one change from balls to convex sets, then one has other kind of properties. If one takes rectangles also, one has other properties. Boundedness properties maybe are different, but are these two things related? I mean, boundedness properties of the,
Look, I mean,
the maximal function with the geometric properties.
I cannot give you a reference, but in general, the Bruni-Kosky inequality is used in all sorts of things that are concerned complex problems. And it certainly guides how much K can overlap with one of its translates. So I can only imagine that it's used in those problems you're mentioning. But I did not give you a specific reference. I don't know this field too much anyway. I find it hard to believe that you're not looking at K minus K in just about everything.
From the historical point of view, one can trace maybe where the Fourier analysis took part in this geometric in this kind of
I think in the 30s or 40s maybe. I mean, people usually cite, the first paper is that's cited in, that's using properties of a Fourier transform of a convex body to estimate the number of lattice points in the convex body. People usually like cite the paper of Hertz. I think it's in the Annals or something like that. And I believe it's before the war, but I'm not sure. But then after that, many newspapers.
Okay. Thank you. Any other?
And there are also some results if you estimate like number of lattice points in the convex sets, and you estimate, then you have to look at the asymptotics for the Fourier transform of characteristic function, and then also there, like you have the first term, and then the second term is like radius to the power 1/3. So
that's right.
So this somehow you have 2/3, but this seems to be
okay, these exponents arise from some level algebra. These are all related. I mean, the asymptotics for the roots of the Bessel function, they all come from the method of stationary phase, which is what is used for the lattice point. This is textbook stuff, really, where the zero comes.
Okay, then thank you again. Continue at 11:15.